introduce Adam Pickarski. He's a grad student at NC State University. He's graduating this year, actually, and his advisor is Ryan Murray. He's going to talk to us today about sorry, can't get it out for some reason. Large limits of t-SNE data limit.
Yeah. All right. Thank you very much, Jeff, for the kind introduction. Yeah, so like Jeff said, I'm here to tell you about large data limits of t-SNE, and I'll go through about what that algorithm is and what it's used for, and really some theoretical math that we do, and maybe some algorithmic ramifications, including some work really more theoretical that me and Jeff and my advisor have been working on. So if I can get things to work. So to start off, t-SNE is an algorithm for data visualization. And data visualization it can be understood pretty simply as you have some high dimensional data. Here we have n samples, and it comes from RD. D I use for data. So D is the high dimensional space, and n is the number of samples. So we'll just use these things like as assumed you know which numbers mean what, or which symbols mean what throughout. And the goal is to find a lower dimensional embedding of this, y1 to yn, corresponding to x1 to xn, which represents some structure, some form of structure of the data set. You're really like kind of thinking the overarching goal is some sort of pattern finding. You want to be able to draw conclusions from your data. And of course, when you're doing visualization, you need m to be equal to like 2 or 3. And the thing is that people in like medicine or biology have really clung on to a lot of these algorithms because they'll use them to make deductions about like very high dimensional cell data. So this here is an image of a mouse brain. So they take and I'm not going to tell you the right way to do it because I'm not a biologist, but they do some sort of processing to the cells, and then they can represent them as very high dimensional data points. And then they have a billion, different cells, and they want to visualize them. And so they'll say stuff like, oh, well, these green cells are like these blue cells because they're close by. And it also appears that these green cells sort of bleed into the blue cells. And I looked in a little bit what they say that means is they'll say like, oh, this means that these green cells may have evolved in some way to these blue cells. And then they'll use it to say stuff like, oh, well, then maybe this is where like a cancer started or something like this, for example. And they'll also say stuff like, well, these blue cells are much different than these like seafoam green cells, I guess, because they've gotten embedded into much different locations. And the thing about this is that you really want to be making sure that if you're doing qualitative deductions from an embedding, that it's reliable in some way. And this is kind of the overarching motivation for us. So to start off with a simple example, probably a lot of people have seen in this room is visualizing the MNIST handwritten digits. So if you're not familiar with what MNIST is, it's take a 28 by 28 grid of pixels, and then there are 70,000 digits from 0 to 9. Each one is considered to be a point in 784 dimensional space, like 28 by 28. And the goal is to be able to somehow draw patterns in this data, say, visualize it and maybe say that 4s look like 9s. This is oftentimes what happens. Or that 1s look a lot like every number in some sense, because every number can be drawn with starting with a line. And be able to say certain things like this. And the first thing people considered a long time ago that everyone here probably recognizes is PCA. And this is a very simple loss, and the structure that they're trying to preserve is inner products here. And what they're saying is that I want to best match inner products across all pairs of data points, right? And I'm optimizing over these variables again, right? And I do it with respect to some squared loss. Now, the thing with PCA is that it doesn't really do very good for visualizations. What you can see is that so these are the colors that correspond to a number. So 0 is blue, orange is 1, etc. And each one of these particles here represents a particular handwritten digit that somebody drew in 784 dimensional space. But what you see is that these kinds of things just seem to give out noise. It doesn't represent any underlying structure in the data. And how are you supposed to make any sort of deductions from a plot like this? You kind of are hard pressed to do so. And so ideas came along that what you should do, a better thing to do, would be put an emphasis on local structure over overarching global structure. And if you do that, you can obtain things that do something closer to this and partition the data a lot better. This is an evolution of something like t-SNE. It's our version of t-SNE, but that's not important right now. But the point is that it clearly does a much better job of partitioning the data. And this is using this sort of theme that local structure is much more important than global structure if we're wanting to represent high dimensional data. And you can imagine why that might be the case too, right? Like if everything is far apart in high dimensions, you have to really be looking locally in order for things to kind of be meaningful. So what we're doing today is large data limits of this algorithm. It's something I know Jeff does a lot of, and probably some other people in this room have looked into. But of course, like just to remind you why you would do something like this, I mean, especially importantly for data visualization techniques, where you want to be able to say that I'm doing some statistical procedure, and underlying that statistical procedure is some model. Maybe it's oftentimes given in the forms of like a variational energy, right? And in doing that, you can effectively say that the minimizers of the discrete problem are something like the minimizers of this continuum limit. And this kind of gives you a stability across experiments, because you're saying each time that I do a statistical experiment, I'm essentially approximating this continuum limit. And so the things, variations between different data drawn from the same population, you would expect to give similar results. And of course, this is extremely important in data visualization, because imagine if all of a sudden your embeddings where two cells were originally here, now give another embedding where they're here. And now one scientist says that those two cells are very similar. Another scientist says that they're very different. And it's just based off the random nature of the algorithm. And you want to be able to rule this out. This actually is a hard question. This isn't what we addressed today. We addressed the underlying model. But that's kind of it's kind of like why this is really important for data visualization, why large data limits are really important in this context especially. So to get back to this like emphasis on local structure idea, the kind of direction that the field moved in was they started doing these neighbor embeddings. And what a neighbor embedding can really boil down to is two-phase algorithm. The first phase is the graph construction. Typically, this is done with a KNN, but the point is that they have some kernel. This kernel really only applies to the k nearest neighbors, but for our purposes right now, you may as well just assume that it has decay enough that if something was outside of that nearest neighbor threshold, that it would cut it off anyway. Here, like these kernels are not increasing, they're decreasing, right? So like think Gaussian, think indicator function, something like that. One thing that actually you notice if you start to read the more popular papers in the dimension reduction kind of field or data visualization fields is that all of them have this interesting self-tuning aspect where the bandwidth actually is localized to the specific point. So Xi only has a bandwidth dependent on himself. So if I'm, and the philosophy for this is like, if I'm standing here, I want to have approximately 5 nearest neighbors. So my bandwidth is, that big. And if I'm standing over here and I want to have 5 nearest neighbors, my bandwidth needs to be much larger and to encompass that, right? So this is really because you want to be able to have some sort of way of saying, well, each data point is related to approximately the same number of other data points. And that's where this becomes really important. And all algorithms these days do this. And of course, you'll see, maybe you already see why, but it will also depend on n, right? As the samples become larger, you expect to just be able to kind of make this bandwidth smaller. And that's crucial for us. The second phase of these types of algorithms is an energy minimization. So they construct some energy. A lot of times this energy is based on the philosophy that there's some underlying lower dimensional graph. They do a graph construction there too. And what they want to be able to do is to match the edges of the high dimensional graph with the edges of the low dimensional graph. So they construct weighted adjacency matrix in the high dimensional space. They construct a weighted adjacency matrix with a different kernel, which doesn't have to be self-tuned because you're just embedding onto the manifold R itself, or R2, right? Which there's not some sort of really complicated, local variations going on in R. So that's why they don't really need a self-tuning there. But yeah, you're really trying to match the edge weights. So it's like a quadratic problem or whatever. Another perspective of this, which will be useful for us, is that matching edge weights is equivalent in some sense to saying if I'm close in the high dimensional space, or if I'm related in the high dimensional space, I want to bring the 2 points in the low dimensional space together, subject to some overall smallness penalty. The smallness penalty is crucial, right? Because if I just have to bring things together with no smallness penalty, then the minimizer is going to be a single point. Everything is just going to collapse on top of each other. So you really need the smallness penalty to get some non-degenerate visualizations. All right. So now if we turn our attention back to actual t-SNE, the graph construction for t-SNE is a little complicated and it's a bit convoluted, but ultimately what they're doing is they're taking a Gibbs distribution over a particular point to all its neighbors. So they, these are Gaussians. And so they use the Gaussian kernel with a bandwidth that will later be tuned into, how we'll specify will be really revealed in a second. And they normalize row-wise so that conditional on being at xi, I have a probability distribution. So you may as well think of this as, the probability condition, the conditional probability that if I'm xi, that I'm related to neighbor j. That's how you might as well think of this. Now, the ultimate question is, how are these sigma I n's constructed? The philosophy for this was that you want to sort of hold surprise constant, and surprise is entropy. And so I want to be able to be the same amount of surprise across every I. So that's equivalent in some sense, they say this is in the paper, is equivalent to saying, roughly speaking, a smooth version of nearest neighbors. So they want to be able to hold basically the number of nearest neighbors constant in some smooth way across all points I. And this kappa for us is going to be that number of nearest neighbors that we're trying to kind of achieve. All right. This is also done like, okay, I'm not writing here, but these PJIs, obviously they depend on the sigma I. So then when they do this in practice, they do this as a binary search, say. Anyway, and then the last thing they do is they symmetrize the weights, right? So you have n of these, each of which sums up to 1. Then you symmetrize them. So you have 2n ones. And then in order for the overall thing to add up to 1, you have to divide by 2n. But this kind of was really crucial for the development of this algorithm because they were able to then say, okay, now this forms a probability distribution over the edges. And then this leads to like natural energies like a cross entropy or Kullback-Leibler divergence. So this is kind of, in my opinion, what maybe Jeff Hinton was thinking when this algorithm was constructed. So anyway, you move to the energy construction phase, which involves a lower dimensional graph construction. And he had to overcome the crowding problem. So I'll tell you what the crowding problem is briefly. There was a predecessor to t-SNE and it was called SNE. And in SNE, there was Gaussian tails in this lower dimensional space. We'll see in a second, these are key distributions. And for some reason, he saw that this caused plots to appear crowded. Things wouldn't separate so well, and data like clusters seem to be on top of each other. And so the philosophy was, well, we still need to make a probability distribution over edges. And furthermore, we want to be able to account for the generic high dimensional distances so that if they're extra far, because in high dimensions, all distances are far in some sense because RD is so vast. And so they wanted to basically say if something is extra far, then we need to be able to extenuate that somehow. And so this was sort of the philosophy why we use a t-distribution, because if you think back to the previous slide, you're trying to match basically Qij to Pij. And if you have a distance of this far in the high dimensional space, xi to xj, it's like this distance, and this is the corresponding Pij. Well, in order to match this with the T kernel, because it has much fatter tails, you have to go all the way out here. So it kind of has this bias towards spreading things further if they're outside of this threshold, right? And if they're inside, then it says, oh, well, maybe they're relatively closer. and we should bring those together. This turned out to be a crucial observation. So we'll take a variational perspective and we'll replace those yi's with a mapping, right? And then we want to construct some variational energy that's a function of t. And so the energy construction, like I already alluded to, was going to be a Kullback-Leibler divergence, because now they're comparing probability distributions. And it's obviously a pretty natural choice to compare P and Q. And this is now really kind of common knowledge, I guess you would say. It's not hard derivation at all, but the perspective that people take when looking at these algorithms is a lot more about this formulation, which is you can view these dimension reduction methods as a sort of attractive, repulsive competition variational problem. And like I already said, so there's basically some term that says, if there is an edge in the high dimensional space, I want to make things close. This, of course, is happy when Txi and Txj are the same, right? That's when this is minimized. And subject to some basically like agnostic global penalty that says, I just want to make sure that everything doesn't collapse on top of each other. So this is the -1 here. So this is log, this is happiest when it's log of 0, because then it's minus infinity. And in order to make this sum 0, I need to make the denominator as big as possible, which is corresponding to super spread out embeddings. Okay. And the thing about this, like I said already, my talk is about large data limits. And it looks as if this 1 over n should normalize with this sum. These pj given i's, they all add up to 1. So this should sort of take care of this sum. And of course, there's this 1 over n squared here. So it should take care of that sum. And it appears as though you would just expect the law of large numbers to kind of get your way through and just be able to turn those sums into integrals and kind of call it a day, and then do the concentration inequalities as this being your candidate limit. But that turns out to not be the case. People did consider this model recently. And the thing is that they, in order to make this work out, they had to assume something about that number of nearest neighbors that I'm holding constant in the couple slides back, where I was picking the bandwidths. They assumed that that was order n, which if you think about, that's going to then cause the graph to not be sparse, right? If you have a fixed number of nearest neighbors for every size data set, then your graph is going to be order n. There's going to be order n entries. It'll be sparse. But if you let the number of nearest neighbors for a particular point grow with n linearly, well, then your graph is going to be, filled up with n squared entries, and it's going to be not sparse at all. And so this kind of explains why this energy that they arrive at is completely non-local, because this graph limiting object is not sparse at all. However, as I already alluded to, this picking of the bandwidth is absolutely crucial. And so I'm going to show you, like, if, maybe you already see it, but it's pretty clear that if you want to hold the number of nearest neighbors fixed and you take more and more samples, what's going to happen is that the radius to encompass k nearest neighbors is going to go down monotonically in n. And actually also it's going to depend on the density at that point, right? So this is, of course, like you could maybe see what's going on. It's like these are the radiuses to, I think, 30 nearest neighbors in this picture. And where the densities are high, the radius can be really small. And where the densities are low, the radiuses are pretty large. So it's, of course, inversely proportional to the density. So yeah, the bandwidths, though, they go to 0. And that's crucial for the graph to remain sparse, right? This is kind of maybe not surprising to you if you've seen any of these k nearest neighbor large data limits. You actually can't let k be completely constant, because you get usually like you can't get consistency that way. But you definitely don't let it grow linearly. You let it grow logarithmically. You just need this in order to get any results, basically. And I already said this. Those guys, they let the number of nearest neighbors grow linearly. So the first kind of observation is just that you have a formula for the limiting bandwidth. So the way that this you can interpret is that like those bandwidths that are chosen via the binary search, you can assume that there's some random part, which is the sigma hat, and there's some deterministic part that's going to 0 at the same rate for all data points. And that's the HM. And if you choose the sigma IN so that this is exactly equal to kappa times like log n, well then as a consequence of holding this constant, the bandwidths will go to 0. And such as this is a common kind of thing to pop up. And you get an exact formula for the local bandwidth, which is kind of the result after you take out the part that's going to 0, which is basically just affirming that the bandwidth that you find with your algorithm inversely depends on the density, right? Rho is my density. Okay. But the point from this all is that like you can verifiably show that if you're doing the procedure that's used in practice, your bandwidths are going to go to 0, which really makes a lot of sense. But this leads to a really striking consequence. It leads to the fact that if you want to do a large data limit, you can't. What's going to happen is the graph edges, weights, they're proportional to a Gaussian with a particular bandwidth. This bandwidth is going to 0. So you might as well think of this as the only things that are contributing to this sum here, which is a weighted sum of pj given I, is going to be things within sigma in distance to xi, right? So that distance going down, you can do a Taylor approximation, right? Roughly speaking. And you can Taylor approximate this because you know that this distance is going to be really small. Well, you know the xi to xj is going to be really small. And correspondingly, this is basically the xi minus xj, right? Maybe there should be a bound here, but for understanding's sake, it's sufficient. Now, the thing is that you look at from this is that now this 1 over n cancels and normalizes this sum. You have an integral, but then inside your integral, you have this bandwidth, which is going to 0, verifiably. So that means that the attractive term vanishes in the limit. And the only thing that you have is repulsion. Which basically, how do you get to the minimizer of repulsion of a repulsive energy exclusively? You just push everything out. And so as the repulsion gets stronger and stronger comparative to the attraction, there's no way I can not push things further and further out. So there's no limit actually. And we can show that actually you can't even get limits in any, like in a reasonable function class. You can't have pointwise limits in L infinity. So it's not like this is like, contrived in any way. It's really kind of not posed correctly if you want to do a large data limit. So this, by the way, actually is an explanation for a technique that always comes up in practice. So what they do with the t-SNE algorithm in practice is they say, well, for some reason, I need to turn up the attractive forces in the early stages of the gradient descent. And we call that early exaggeration. And if I don't do that, then my plots look terrible. And to us, this is basically they're turning up the attractive force. To us, this is kind of verification of our theorem here, which says that asymptotically, the attractive forces vanish. And so in order to compensate for that, of course, they have to turn them up in the early stages of the algorithm, right? So the first kind of way that we tried to combat this issue was to just take a sort of simple approach and just rescale the attractive term. This is now I'm rescaling with respect to the thing that's going to 0 at the same rate across all things, across all data points, just so that this is going to 0. And so now this thing on top, which was originally going to 0, is basically going to be like a derivative now. And that combats the fact that this attractive force vanishes. And it turns out that if you do this, well, then you can get pointwise consistency results to a Dirichlet energy plus some non-local repulsion. And this is really, this result is not very difficult to show. It's just a pointwise result. We're, yeah. But it's just about kind of getting it into the right form here. So, oh, and the other thing about this is that this energy is well posed, like in H1. So this kind of is at least some sort of validation that you've converged on something meaningful, okay? But let me talk a little bit more about what happened when we use this energy to inform us for algorithms, okay? So the idea is just now this A tilde was rescaled. And so that thing that was originally a log is going to be Taylor expanded to just the quadratic. So now my attractive force is quadratic. And if you've seen graph Laplacians, you can easily write this. Quadratic losses correspond to graph Laplacians. So you can write this in terms of graph Laplacians. And so then we decided, well, what if we tried to decompose the graph Laplacian matrix, like do a singular value eigendecomposition, and write the solution. This is the collection of all y1 to yn. We write the solution as a linear combination of those eigenvectors. Because now, if we do that, you can only be optimizing over the parameters. And the parameter space is much smaller than optimizing over every, particle. You have n particles. This n is a lot of times in practice like a million, maybe even a billion. But if you have, this is constant order now. Okay, so seems very promising. And it is to some extent. It also allows you to be able to approximate the repulsive term in a kind of meaningful way, because now your repulsive term is dependent only on the y's. You just wanted to make a global penalty in the embedded space. And this was originally an n squared operation to compute, but now that the y's have a relationship with the x's, you can kind of faithfully subsample and approximate this term pretty well. And so then you don't have this n squared computation here. You minimize this loss over theta, and you've kind of reduced a lot of your computation. So everything seems really good for us. And I'll mention that the reason I put k here instead of the original kernel was because it happens that if you mess with this kernel and make it sort of non-smooth, you get a little bit better results. This, by the way, kind of is alluding to the next thing that I'll say, is that if you've seen a t-SNE plot, this kind of doesn't look too great. This doesn't partition the data set as well, even as the evolution that I showed in the first slide, or second slide, which seems like maybe there's a problem with this Laplacian approximation. So now we're going to turn back to the crowding problem. And again, the crowding problem was that plots appear crowded because all distances in the high dimensional space were too far away. Now, it turns out, actually, that the crowding problem interpretation, the original interpretation, isn't actually what I like to interpret it as now. I think of the crowding problem, it turns out that t-SNE also, regular SNE also had quadratic attractive forces. And the funny thing about a quadratic attractive force is that, say you're doing a KNN graph construction, and you have a 2 moons data set, right? Well, you're inevitably going to get sort of this spurious edge if you want your graph connections to be on manifold. You can't do it with KNN, right? And so then your graph that you're going to embed later has these false positives, if you will, which will try to spread out, but kind of can't, because the attractive force scales linearly with the distance. So as they kind of try to separate off, they start to get pulled back stronger and stronger. And this appears to make the plots seem really crowded. And if you contrast this to what t-SNE's forces are, so t-SNE, remember there was a log of 1 plus y1 minus y2. So when you take its derivative, this is what you get. And the thing about this is that if there was an edge in high dimensional space, Pij was positive, but it was a faulty edge, well, the same thing happens where I want to spread this false positive out in the embedded space, but eventually I come to a point where this denominator kills the kind of contribution of that faulty edge. And it allows things to spread out. And so what this graphic shows, when you compare it to the last one, is here you have attractive forces. Now I'm just plotting the attractive forces. And the weakest kind of attractive forces are blue and the strongest are purple. So you could see that like the strongest ones are, of course, intra-cluster. They go from cluster to cluster. This kind of indicates some faulty edges. It inverts when you use the t-SNE attractive force. The strongest edges are inter-cluster. intercluster. Now, this seems maybe like it has a bias towards clustering, potentially, but it's something that we're still investigating for sure. But as you see is like, now the intra-cluster forces are far enough that they become weak. And then when you apply repulsion, it's able to split these. And that's why if you've ever seen a t-SNE plot, they become really well partitioned. And that also explains why the Laplacian force is maybe not the right thing. Although I have recent results that have fixed this, and I'd be happy to talk about them, but they're very recent, so I'll have to talk about them afterwards. But this kind of brings us to the last point of the presentation, which is about the stuff that Jeff and I and my advisor Ryan have been working on, which basically boils down to saying, well, modifying the attractive force was artificial in some way because I'm changing the energy. And we kind of confirmed that by seeing how qualitatively different the forces are in the behavior of the plots, of the resulting plots. And so it was kind of artificial. So maybe the right thing to do to combat this asymptotically decaying attractive force is to allow your plot scale to go bigger and bigger. Because now if things are really far apart in the embedded space, well, I can make the attractive force really large just because now that they're far apart, the attractive force is growing linearly with distance. Well, logarithmically with distance. But nonetheless, it grows as you grow the distance. So it turns out that this is a faithful way to recover a probably better underlying energy. So if you basically all I'm doing is saying I let t be divided by h and I let h go to 0 so that I expand my plots indefinitely. And what do we get? Here you see that what doesn't happen is the log vanishing. So this log, which seemed to be really important from a qualitative perspective on those plots of the forces, does not go away. And in addition, the repulsive term becomes completely localized because this starts to look like a Dirac mass because txi is only contributing to txj if it's order h and h is going to 0. So this starts to look like a Dirac mass. And then using some co-area, you can turn it into this formula. And so the overall energy is like this. And you can sort of, if you want, pull this log back in and see this as a quotient of the sum of eigenvalues or eigenfunctions of the Jacobian t divided by the determinant of the Jacobian. Which kind of, if you've ever seen quasi-conformal maps, is similar to the definition there, which I link back to, not because we have results on this, but it intuitively makes sense because quasi-conformal maps seek to approximately preserve angles. And it would make sense if this visualization method was doing something similar, but on a local level, right? And there's a lot of open questions here. It's obviously a really weird energy, so existence of minimizers is not clear. The coercivity due to the log is not immediate, so you don't have a real good function space to work in. And so you're kind of stuck. Even though you can get sort of lower semi-continuity, you don't really have a priori function space bounds because the log permits discontinuities. So that's kind of tricky. If you were able to get this, then you would naturally do discrete continuum limits and then kind of answer the overarching question of whether or not repeated experiments lead to similar results. Evolutions equations would also be interesting. And maybe if this can give some sort of algorithmic insights, that would also be, of course, useful. But now bringing to the stuff that we've been more recently working on with Jeff is we kind of simplify this for a little bit and look at a one-dimensional model. And it turns out that if you set D, the high dimensional space, and the low dimensional space equal to 1, then the energy only depends on the gradient of T. That's what I'm calling U here. And you get this. You still have the problem of a lack of coercivity, but it turns out that we have a pretty good idea that there's going to be a unique minimizer of this. And so we get sort of an existence and uniqueness result for this energy. Of course, this doesn't kind of answer the question for higher dimensions, and that looks really tricky. But yeah, this is about what we have. we'll show you really quickly. This is kind of a nice way to circle back. If you plot, say, a Gaussian, and then you plot the minimizer associated with the push forward of this energy, well, you get something with fatter tails than a Gaussian. It's obviously not the T distribution, but it does sort of spread things out a little bit. So it's a nice way to kind of bring back to the fatter tail idea, if you like. But there's no closed form for this right here. But anyway, that's about what I've got, and really honored that you guys have had me. So thank you, and I'd be happy to take some questions now. If they have some.
Questions for anybody on Zoom as well? I can ask some. So in your first part of your talk, you said that right, that your observation that the attraction is weaker, sort of vanishes in the limit, kind of explains early exaggeration, right? So does it explain like why they have to turn it off though?
Well,
they don't run forever, right?
Yeah, it's a good question, right? And the way I've been probably link back to this, I would say that in doing early exaggeration, you're looking at this force diagram. And like kind of we said, this gives us a decent initial kind of point. But then they turn it off so that they can get to these attractive forces, which are, capable of breaking ties. Once they turn it off, they're back in this logarithmic attractive force. And of course, the ties are able to be broken now. So that's like my interpretation of why they must turn it off, because otherwise you're stuck here and where outliers are really heavily kind of cluttering your plot. Yeah. Thanks for that question. That's a good question.
There is a couple of things I'm doing here.
Okay.
So what about our energy as humans? Not sure.
Not sure. That's a hard one to answer, I would say. It's very subjective. Depends on your perspective.
Are there any other questions from people in the audience?
Yeah.
Great talk. Thank you for answering. So you say that you have some preliminary result on the existence of unique minimizer in D1. Could you talk a little bit about preliminary result? And you think also you can prove like convergence rates in dimension 1?
I'm not sure right now about convergence rates. I guess so. Like the main issue that happens with the 1D model is that like you lack coercivity, so you can't really just use the direct method. What we kind of found was that if you try to take the first variation of this, it has a unique solution. And then what we wanted to basically do is some sort of gradient descent to show that any initial condition converges to that, unique solution of the critical point. But the problem is that the gradient descent scheme actually isn't monotone in a decreasing energy way. So we had to truncate the gradient in sort of a clever way to make sure that that energy decrease was monotone. And that kind of, energy is monotonically decreasing and it comes to a stable state, which we know is the unique stable state, then we can basically say that it's the unique minimizer of the second field. But yeah, and then there's really a hope that that would translate over to the high dimensional case, but definitely not like clear, because what the biggest difference probably with the high dimensional case is that you can't just replace the term that depends on the gradient, because you also have this sort of non-local dependence in a parameter due to the co-area, which vanishes when d equals 1, and it's the same. Which makes it so like it's not as clear as whether or not the same thing will work, but it might. Yeah. Good question. Yeah.
So going back to the beginning, so for SNE you have Gaussians and T, and then you have ones with the N that's slightly different. So is there a way of figuring out how to optimize the distribution, which presumably depends on the data itself?
Yeah, it's a really good question. And so here I'll give you an answer. What I have recently found was maybe a better way of doing that question isn't to introduce a new kernel, because that kernel may be susceptible to spurious breaking, like we saw. So what I have recently realized is that these plots, like you see here, actually you can check to see. Of course, you don't have access to label data, but you can check what is the probability that I've mislabeled something if I have a really high distance as a result of my embedding. And it goes up to like 100 rapidly. And so what I do is I take that fact as a way to prune my KNN graph, and I renormalize the weights in a way so that the net attractive force per row is approximately the same. And then all of a sudden things start to really partition well, and you're not in this crowding problem regime. If I were to make a pitch as to why that may be a better alternative, is that you're still starting with the same KNN graph that you're using for t-SNE, but you're not susceptible anymore to these maybe arbitrary breaking of ties. So yeah, it's a great question. And people have tried a bunch of different things. Yeah.
I mean, I guess another natural question is about UMAP, right?
Yeah.
Which is maybe preferred by a lot of people.
Yeah. So yeah. So
Anything about that as well?
Yeah. So if you've seen UMAP, they use a very similar sort of particle flow to t-SNE with two kind of tweaks. One, the attractive force is a bit different. Like the kernel they have a hyperparameter there, and so then they use like least squares to find the hyperparameters. Well, there's some sort of like hyperparameter that you have to decide as the user, but they use hyperparameter to basically figure out the coefficient around this, what it's raised to down there. They also in UMAP, in the repulsion term, it's not just kind of agnostic to the high dimensional data. They use a 1 minus PIJ essentially. And so they're saying like, if there was a neighbor in the high dimensional graph, I want to repel these two less, right? And this kind of seems to lead to empirically better results. Actually, people have taken this one step further and said, well, what happens if we even intentionally tell far points? They somehow mine for far points, which all they're doing is just not choosing some of the first nearest neighbors and intentionally repel those points. And in doing so, they actually get even better clustering. So this is this is kind of a progression I've seen of these types of algorithms. So they keep getting a little bit better for these like MNEST, and then it's not clear how well that translates to practice, but like, yeah. So,
Any other questions?
So, yeah, so actually listening to your talk, I don't get a good impression of t-SNE after all. You know, there are many issues which are not completely clear. And, you know, you mentioned the issue of attraction, and after all, people are using some heuristic to get over it. So from digging into it, can you come up with better procedures?
algorithmically?
Yeah.
So yeah, if I were to come up with a more meaningful algorithm, it would be right now, what seems pretty promising is to do this sort of edge pruning on faulty positives, because then you can say, well, the graph that I have in the graph Laplacian eigenvectors are just higher fidelity. Yeah, and I would argue that's a better interpretation than like.
And which energies are you going to use?
Oh, I would use like the Laplacian attractive force, and I'd use a hat kernel here. Like I didn't make this super clear, but it's just like a hat. For some reason, this seems to do pretty good at repelling things. Yeah.
And to get an estimation for this probability, because currently, you know, you said you can get it from ground truth data, but how would you really get this? So
I wouldn't. But the thing is that I can use that on faith to say that if I remove an edge, it's a very high likelihood that it was a sort of an intra-manifold edge. Because if you remove one that was like a true positive, you still have so many others that it doesn't really mess things up.
Okay. What about doing message passing to get some better estimate of this probability?
Oh, as in like random walk?
Yeah,
Sure,
some
to make it
sort of-
So I have considered that. The reason I haven't tried that yet is because I just kind of assumed that that might be computationally expensive. But yeah, I had considered the same exact thing. Is like that seems to be a way that would combat that kind of faulty edge construction for sure. Thank you. Yeah.
I really like all the pictures, like it's cool to like be able to visualize these things. I guess I have a question of, do you have any way to like quantitatively say this is a better embedding, or is it all based on like, I like the way this one looks better?
Yeah, absolutely. Great question. So there's kind of a couple of benchmarks that people like to point to. So one is like a KNN classifier error. That's sort of fallen out of favor, and what people prefer is to use some sort of KNN recall, which you know what a KNN recall is. Basically, it says like, okay, I have the k nearest neighbors for xi in the high dimensional space, and then what nearest neighbors do I get in the low dimensional embedding? And if they match up in some way, then that's like their KNN recall. And they do it in sort of in more than one index, and this is kind of what people consider. So that's kind of considered the benchmark. And so what I'll point to, which I don't have here, again, I figured the pruning thing out yesterday, but in doing that, actually it makes the KNN classifier accuracy go way up. And so this is kind of like, you know, good faith that something is working. Yeah, but that's a great question.
There's no other questions. We'll thank Adam again.
Thank you guys.
There are some grad students meeting at 3 o'clock with Adam, so if anyone else wants to join, the other graduate students, feel free. Adam and Vincent, 5:40.
Thanks, you.